So we're going to start talking in greater detail about kinetics right now, and I'm going to use the term Michaelis-Menten kinetics or steady-state kinetics. I'm going to explain what that indicates, why that is important. So first is to do a review of some of the vernacular. Remember, if we had an enzyme binding a substrate. So now it makes this complex where the enzyme and substrate have formed a quaternary interaction. And we'll assume that it makes a product or products that's in a quaternary interaction with the enzyme, and then you get release. Product gets released, you get your enzyme back. So that means the possible concentrations of things that we could have is you could have free enzyme, we could have free substrate. Okay, we're going to be able to have the concentration of E and of the ES complex, and the concentration of EP, and the concentration of product. I'm going to try to keep them color coded as much as possible. Okay, so if we start at time 0, so in the beginning here, and this is just a measurement of concentration as time changes. And I'm just going to arbitrarily, it doesn't really matter where I put this, but I'm just going to say the concentration of the enzyme starts off right around here. So what happens to the concentration of free enzyme as it interacts with substrate? Is it going to go up or is it going to go down? Down, right? It's no longer free. It's going to be binding S. So it's going down. And it doesn't really matter. It's not a big deal like what the slope is here, but it's going to go down. Chances are it won't go all the way to 0. But with time, what's going to be true? Do you get your enzyme back? Right, so it's going to go up, and it should be the same, and I apologize if it's not exactly the same, but it should be the same concentration as it was before. Okay, so I'm just eyeballing it. Okay, likewise, and it doesn't really matter where on our scale we start. I'm just going to make it a little easier. I'm going to say we start off with substrate, the concentration of substrate up here. That's free substrate. So what's going to happen to the concentration of free substrate as time goes on? It's going to go down. It's going to approach 0, but it may never get all the way to 0. I mean, I don't know. That part doesn't matter. You don't get it back, typically. Right? It's going to use up. So that's why I have that. Once again, I'm trying to make these color-coded. Uh-huh.
What was the first line representing again?
Concentration of free enzyme. Okay. So another possibility that we have, which I'm going to do in a different color, is we have the concentration of ES, which I'm going to use as a darker, whatever that color is. And in the beginning, at time 0, what's the concentration of ES? 0, because it hasn't come into contact with substrate yet, right? But then what's going to happen as it comes in contact with substrate? It's going to go up. Okay, it's going to go up, yada, yada, yada. And once again, I don't know the exact concentration where it's going to end, but at some point in time, it's going to peter out. All of the enzyme will be bound, or all the substrate will be used up, or something. It's going to remain relatively constant whenever you're at this section of the reaction mechanism. And then what's going to happen with it with respect to time? It's going to go back down. And in theory, it would go all the way back down to 0. It's kind of hard to say if it goes exactly to 0, how efficient your enzyme is. And so that's what that ES is. And likewise, we have the last one. Oh, actually, there are 2 more. Sorry. We have EP. And at time 0, how much EP do we have around? 0. Now, is it going to go, which do you see first, ES or EP? ES. So it's going to take it a little bit longer. And once again, it may go higher or lower. It's not so important. It's going to lag a little behind. I'm just going to put it here on your notes. That part doesn't really matter. It, too, at some point in time, is going to be at equilibrium. And then it will go down, usually, in theory, once again, it would go towards 0. Whether or not it truly is 0, especially in vivo, it may not be 100%, accurate. It's going to look something like that. And then finally, we have product. What's the concentration of product at time 0? 0. And it's going to take the longest, right? Because you have to form ES. You got to form EP. And it's going to go up. And it's going to end up somewhere up here. It's not going to go back down unless this is a reversible reaction, of course. And it may end up higher than S. It may end up lower than S. That part doesn't really matter. But it's going to end up at some point in time. So that's the concentration of product. Now, if we notice, there's this region of time where the concentration of ES and EP doesn't change. It's flat. So if you think back to calculus, you take the what's it called? The slope of the tangent line, of the derivative. Why could I not think of the term derivative? You take the slope I remember slope and tangent, but not derivative. But you take that slope, and that slope is 0. It's not changing with respect to time, right? And so this region here is called steady state, because what they say is that all of the enzyme-bound intermediates, like ES and EP, or even if you have like a third step in there, like an EX or maybe ES1, ES2, or what have you, all of the enzyme-bound intermediates, their derivative there, they flatline. They're not really changing. They're at equilibrium. So this is called the steady state region. The part that's before that is called pre-steady state. And I guess in theory, but it's not important. So in theory, it would be, I guess. Okay, so this region right here, there's a whole field of kinetics called transient kinetics or pre-steady state kinetics, where this gives you the most information. It literally tells you how everything is changing with respect to time. However, it is the most difficult. It's sort of like, you can imagine you just get the human genome. So they have all the nucleotides and all the genes and everything that there. It gives you all that information, but it's really hard to decipher. Unless you're really looking at something and able to isolate something in particular, it tells you almost too much. This region right here tells you the big scheme of things. How much product, how much substrate is there, and that kind of thing. But so it's easier, and it makes the math much more simple whenever we do derivations in just a moment. That's why it's called Michaelis-Menten or steady state kinetics. However, it doesn't tell you everything, right? We don't know what's really going on in this region, but it's usually utilized as a good marker, a good tool. Okay, so that's why it's limited. It's usually the math and the way to monitor it is usually more simple than doing pre-steady state, but it doesn't tell you all the information that you may need to know. So there are two types of kinetics in general. There's the steady state and there's pre-steady state. There's another one that they do, like I said, it's called transient, where they may even let it go to equilibrium, and then they just perturb it a little bit, and then they measure how everything else changes and stuff like that. But that one's the most complicated. So we're going to really focus here, and your book focuses on steady state kinetics, and it's called, because it was derived, the equation was derived by two scientists, Michaelis and Menten, so they also call it Michaelis-Menten kinetics. And they give this special ES complex, even though a lot of times they still call it ES. Some people or some books may also call it the Michaelis complex. Okay. All right. Now we're going to even make things more simple to derive the Michaelis-Menten equation. Okay, so let me We'll go next. So the Michaelis-Menten equation, I'm going to give you the answer, and then we're going to derive and see what it means. Michaelis-Menten, what it is, and what they say is that velocity is equal to what they call Vmax, which we've talked about, that's as fast as it goes, times the concentration of substrate, over something called Km, which we'll discuss later what that means, plus the substitution of substrate. Okay. This is the same thing as this. Okay. Vmax, and the reason why is I'm going to put way over here. Vmax, the technical term is Kcat times the concentration of enzyme. Okay, so that's why we could even say that the Michaelis-Menten equation is the same thing as saying Kcat, and once again I want to point out that's lowercase k times the concentration of enzyme, and it's free enzyme. Well, I mean, technically that would be total enzyme, I'm sorry. Times the concentration of enzyme times the concentration of substrate, all divided by this term Km, which is a capital K, not a lowercase k. Remember, that's an equilibrium constant, plus substrate. And so if we plot this, this is what it's going to look like. The y-axis is v, the velocity. The x-axis is substrate. And this velocity, what's really important to point out is it's the initial velocity. So like a little side point over here. If we're going to measure, and we started talking about this in the last class, if you're going to measure the rate of the reaction, most of the time what we do is we look at how much product is formed as a function of time, right? And it's going to start off with 0. It's going to increase, but then at some point in time, it's going to flatline. So it's hyperbolic because you're going to run out of substrate. You used all of it up. So if you think back to calculus, the slope here changes, right? So what I mean by that is the slope at this point is different than the slope here, and then this slope is 0. So what velocity is that change, and if you need to put triangles instead of D's, feel free to, but the change of the concentration of product as time changes. It's just a derivative. But the problem with this, once again, is that that derivative changes with time. So to make math simple, whenever we're comparing kinetics, we always compare what they call initial velocity. Some books will call it VI, some may call it V0 for V is 0. Technically, if you think about the calculus, what that is, it's the limit as it approaches 0. But I just want to point out that it's the slope. It's the slope right down here. Whoops, I didn't do a very good job. That's really a crappy job. Here, it's probably easier for me just to point it out. So the slope of this tangent as you get towards 0, that's your initial velocity. It's how fast were you going in the beginning. So you try to do as small amount of time as possible. Okay, so that's your initial velocity. I mean, technically, if you were setting this up as a limit, it would be the limit as time approaches 0. Okay, so velocity as time approaches 0. But it's just how fast were you going, as close to the beginning as possible. On a practical note, usually we would only let like the first 10% of the reaction occur, first 5 to 10%, because otherwise it's going to start to slow down. The apparent velocity will start to slow down. So we would call that first 10% or so the initial velocity. That's important when we get over to this plot. This is a Michaelis-Menten plot. And so what happens is in the beginning, once again, so this would be initial velocity, or V0. It's going to be 0, right, in the beginning, because there's no substrate. And as you add substrate, it's going to get bigger and bigger and bigger until at some point in time, it doesn't matter how much more substrate you add, because all of your enzyme is used up, right? So all the enzyme is busy, until it can get free. So what it happens, and this is the very last plot that we looked at, I think, on Monday, is at this point here, that's your Vmax. This right here is an asymptote. Go back to calculus and think about that. That's called Vmax. Because literally, it's the limit of your equation up here as S approaches infinity. So S is really, really big. So what I mean by that, let me see if I'll let me move everything. Oh, good, it will. So mathematically, what we do is as S gets really, really, really big, the equation here, this equation here, means some way I tried to think of it, because limits sometimes would drive me nuts, is we're saying that the concentration of S is so much bigger. Oops, I didn't mean to do that. Than whatever that number Km is. Whatever that number Km is. Then it simplifies, because what that says is V is going to be equal to Vmax times S divided by S, because S is so big that Km doesn't really matter. So now you can see, well, that's really easy. The S's cancel, and so we say that the velocity is equal to Vmax. Likewise, we can do the same thing as whenever the limit approaches. Change colors. So now if we do as if S is really small, so as S approaches 0, now what we're saying is the concentration of S is much smaller than Km. So therefore, Km plus S is essentially the same thing as saying Km is equal to Km. What I'm saying is this number, I'm just going to make this number up. What if it's 1,000,000, but S right here is like 1? That's essentially the same thing as 1,000,000. 1,000,001 versus 1,000,000. So S is so tiny, it doesn't really matter. So then the answer to that limit would be V. So now I'm back up here. V is equal to, we still have Vmax, we still have S, but now on the bottom we only have Km. Once again, that's a capital K. Like that, the plus S at the bottom doesn't really matter. So whenever we look at the two variables, I'm just going to rewrite it a little differently. That's the Y is equal to Vmax over Km times that. So now it's a first order rate constant, which was in that last picture, that last figure that we went over on Monday. That was whenever they had, remember it had that little line or something here and it said it was a first order rate constant. And that's true because we proved that mathematically. What happens is you get the slope is called Vmax over Km, and it's got a special name for it later on. I can go ahead and tell you what that name is. It's called the specificity constant. And some people also like to call it catalytic efficient, which I like calling it catalytic efficiency. That'll make more sense when we do, I don't know if we'll get to it today. Maybe, but if not, we'll get to it on Friday, talking about what it means to be catalytically efficient. So this is the Michaelis-Menten equation, but now we're going to actually derive it for one of the mechanisms, the simplest of the mechanisms that we could possibly have routinely. Okay. So you guys have your notes where you can go back to the original Michaelis-Menten equation, which is V is equal to Vmax times S divided by Km plus S. So that way I don't have to keep writing it over and over and over again. Okay, so this is the simple equation I was talking about. We have enzyme plus substrate. It's going to bind to make the Michaelis complex. But now what we're going to say is that the chemistry step, like the formation of product, is so fast. It is so fast that you don't ever really see EP. And there are a few enzymes that do this. You automatically get product. Like you can't, like you try to take a picture of it really quick, you never actually see the EP complex because the dissociation of it is so fast. Which, like I said, there are enzymes that do that. And that way we don't, the reason why we want to do this, like I said, this is the simplest of the terms before trying to do the derivation, the calculus behind it. But I didn't want to, the reason we do this is going to make the math more simple. Okay? So, now another thing that they do is each one of these steps, so for example, this step right here going forward, each one's going to have a little k, okay? So what that means is there's a little k here, there's a little k for the backwards. We're seeing the substrate can come off, but there's going to be a little k there. So we have to have a way to differentiate each step of this reaction mechanism. There's this step, and then there's this step. So what kineticists and enzymologists do that are really, I think is cool, is they say, okay, this is k to the subscript 1. So rather than giving each one its own little k with a new number and have to worry here about k1, k2, k3, k4, all that kind of stuff, what they say is this is the reverse of step 1. So they call it k minus 1. So this one just becomes k2. And since we're only looking at initial velocities, we actually don't even have to worry about the backward step here because at time 0, p is equal to 0. So I don't even have to worry about putting in a k minus 2. Trust me, that makes it so much more simple. So this right here is the rate, you remember the rate? So let me write this out again. Rate is equal to the change, and you can even call it velocity, rate or velocity, doesn't really matter. Remember, it's the change in the concentration of P, and if the little d scares you, you can put the triangles, as time changes. So that means we're watching the formation of P. This is the only step, that's the rate limiting step here. Does that make sense? You can only see P based off of whatever this rate is at that time. So that means that this right here is equal to K2, whatever that kinetic rate constant is, times the concentration of something. And what's that concentration going to be? What's the concentration that's dependent, that the rate depends on right now? ES. Right, because that's literally the only thing here. It's the amount of S it takes a concentration of S in order to make product using this rate. So you think, oh, that's nice and easy. You just have to know, if you know how fast it's going, then you see that's K2, life is good. However, there's a little bit of a problem. Almost always, there are very few exceptions, you don't know what this concentration is. Remember, we're making the steady state assumption that the rate of its formation and breakdown are going to be equal. It's at equilibrium. But you don't know what that concentration is. Almost always, what you do know, so what do we know? You know the amount of enzyme that you start off with. Okay, I'm going to call it E total or ET because it's going to get kind of annoying to write the word total all the time. Usually when we're doing this either in vivo or in vitro, especially in vitro, you know how much enzyme you have. You also usually know the concentration of substrate that you start off with. So that's what you know. What you don't know is the concentration of ES. And it's difficult to know the concentration of free enzyme. So what we want to do is put all of this equation to solve the Michaelis-Menten equation. We want to put it in terms of things that we do know. So this is where all calculus is it's just a way to manipulate the numbers to make it into algebra. So we're going to try to substitute E total and substrate concentration for this ES. Since we don't know ES, but we know the total concentration of E and the amount of substrate we started off with. Okay. So I'm just going to rewrite this part just so that way I have it all in one place. We have rate, which I'm going to just call V, is equal to K2 times the concentration of ES. That's the same thing that I had over there. I just wanted to make it a little neater for myself. One other thing that we do know is the total concentration of E. Oh, I said I was going to use ET. The total concentration of E is equal to the concentration of E that's free plus the concentration of ES. Does that make sense? Take whatever's free, you take whatever's bound to the substrate, it's going to equal the amount that's total. And then we have our steady state constant. It's called the steady state assumption. So I'm going to write it out. And it sounds really scary, but once you think about it, it's not that bad. What it says is the concentration of ES with respect to time is equal to 0. Which, remember, we drew that early on at the very beginning of class. So what does that really mean? That steady state assumption. So to put that in real term, like simple terms, what that means is the rate of formation, which I'm just going to say rate of forming ES, has to equal the rate of breaking it down. Which kind of makes sense. That's why it's called steady state. Just as quickly as you form it, you break it down. So apparently it looks like it's not changing. In reality, it's dynamic. But it's just that just as quickly as you make it, you break it down. Okay. So what is the rate of formation? Which I'm just going to call it V forward. So this is the ES. Which little k's point toward the ES? K1. Okay. Then, because remember, every rate is equal to V is equal to at least one little k, if not more than one little k, times a concentration. So when we look here at how to make ES, its formation depends upon the concentration of what? E plus S, E and S. So that means you literally, because it's second order reaction, if you think back to Gen Chem, this is what it looks like. Then we have the way to break it down, which I'm going to call it V reverse. So now we have to look at the ways to break it apart. So now, how many arrows go away from it? 2. We can either go forward to make product, or we say that, you know what, that substrate could fall off and it goes backwards. And it doesn't really matter which one we start off with. I'll start off going forward. Okay. So to go forward, what little k is that one? That's K2. It still has to have a concentration dependency. What does its concentration depend on? ES. You can't break it down unless you had it to begin with. Right? Now you just have to put a plus sign. What's the other little k that affects it? K minus 1. And the concentration for its dependency is, it's also ES. It's just that you're going in reverse. See, concentration going backwards that way. Because your book, I think, just gives you, it skips a lot of steps, and I know the PowerPoints also do. So that's why I try to explain where they get the numbers and stuff. Okay. So, what does this mean? We can actually go ahead and simplify this one. Since we have a whoops, that's not it. Since this is the same thing, since there's an ES here and an ES there, here's an ES, there's an ES, everywhere's an ES, we can pull that out. And you get, whoops, K2 plus K minus 1, which I didn't leave myself much room, so hopefully you left yourself more room. And the reason why I want to do that, I just want to point, is remember up here we have the ES by itself. So we want to try to solve for ES. So now, based off of this right here, where the rate of formation has to equal the rate of breakdown, remember, we know ET and we know S. We're trying to find ES, essentially. We can now start putting these things together. The rate going forward has to equal the rate going backwards, so therefore what that means is we have K1 ES is equal to, I'm just going to keep the same color, K2 plus K minus 1 times ES. Okay. So what I'm going to do now is I'm going to solve for a free enzyme. Because right now we still have two unknowns. We have one known, the S, but we have two unknowns, this free enzyme and free ES. And if you think back all the way to algebra, you want to try to get it down to just one unknown, right? One variable. Try to solve y in terms of x or so on and so forth. And so we can actually do that by dividing both sides. Remember, whatever, just go back to algebra. Whatever you do to one side, you do to the other side. So to get the E by itself here, we have to divide by K1S. So I'm just going to divide both sides by that, and I get the concentration of E is equal to, oops, I didn't leave myself much room, this term, K, 2 plus K minus 1 divided by K1S, sorry, it cut off. It's a K1S times ES. Let me see if it'll let me. There we go. K1S. Everybody moment to get caught up. So now let's go back to our ET, our total enzyme equation here. Because remember, up here we still had two unknowns. We had an E and an ES. Now we found a way to relate E to ES. So we just do the mathematician's favorite game of plugging and chugging. So I'm going to move this all up a little further. And now what we can say is that, sorry, remember E total was equal to free E, which we just solved for, K2 plus K minus 1 over K1S ES plus ES. So look back at your notes, because unfortunately I had to move it up there. But remember, the total enzyme was equal to the amount of free enzyme, which we just solved for, plus the amount that was already bound. Okay, so now what we're going to do is we can actually simplify this, even though it may not look like it's going to be simplifiable. Simplify, that is a word, right? Simplifiable. It just sounds kind of funky. We can pull out ES. So E total, I don't want to keep rewriting it, is equal to the concentration of ES plus times all of that. Whoops, sorry, I didn't have it. All of that plus 1. Okay, so let's rewrite that. So we have all of those little tiny K's. K2 plus K minus 1. Divide that by K1 times S plus 1. So that's the total concentration of E. So just to review what we've done so far, remember, we knew the amount of total enzyme, we knew the amount of substrate, we just did not know E or ES. Now, what we've got this, we've narrowed this down, whoops. Oh, let's try that one. I haven't tried. Now we've narrowed this entire thing down to where this one we know the total concentration in enzyme, we know S, we only have one unknown variable. So that's really important, because if we go all the way back into the beginning, remember we're trying to find ES. We now found it. So I'm just going to rewrite it. So to find ES, we just divide both sides by everything that's in that parentheses. All those K's and the 1 and all that kind of stuff. So it means it makes it really ugly looking. But what it means is that we have E total. Let's look at my notes, because in my notes I skip steps, and I try not to skip steps whenever I'm working with you guys. We have E total divided by 1 plus K2 plus K minus 1 over K1 S. Okay. Alrighty, so what we're going to do now is I want to try to simplify this. Yeah. So, because we want to try to simplify this in terms of, remember, you can multiply anything as long as it's equal to 1. So what I'm saying is, if we multiply this entire thing by, how can I explain this? Let's see. K1S over K1S. So if we multiply this, because it's the same thing as multiplying it by 1. See, K1S, K1S. That's the same thing as multiplying something by 1. But we do that, we can get rid of this down here. Does that make sense? Because you want to try, if at all possible, we want to try to simplify things from having denominators on top of denominators, or underneath denominators and beneath denominators, and it makes it a little easier. And so what that does is now the ES that we just did is going to be equal to K1 S E total over, and on the bottom, when we multiply this, K1S plus times 1 is going to be K1S. But now we're just left with this K2 plus K minus 1. Doesn't look quite as scary, hopefully. I really wish that this little blackboard thing here was so much bigger. That way I could... Oh, that's what I was afraid of. Oh, there. Oh. Awesome. It takes very little to impress me. Okay, so what I'm going to do now is start to put all this back into the equation that we had before. And I want to do, I'm going to do something. So if you notice here, we have a K1 on top and we have a K1 on bottom, but we don't have a K1 there. Okay, but the reason why I wanted to get rid of it is because in our original equation we have an S. Like if you go back to Michaelis-Menten, remember it said Km plus S. So I want to get the S all by itself. So let's factor out that K1. So you can factor out, like the K1s can all cancel, but whenever you do that, this right here turns into the following. So what I'm saying is we're going to cancel out the K1s, but to cancel out that K1, we have to divide the K1 there because it doesn't have the K1 on it. And so this becomes S times E total over S plus all of that jazz. K minus 1 divided by K1. See, all those little K's are ugly, but we're going to get rid of them in just a moment. Just like, I don't want to say a cheat way. But see, we can't cancel out the two S's because there's not an S there. That's why that S gets stuck. But all of this was equal to ES. So give me just a moment. We know this one, we know this one, and we know this one. So we now have put ES in terms of everything that we do know. So in your notes, just quickly look back there to see that original rate equation, which kind of gets hidden up here. Remember, V was equal to K2 times the concentration of ES. So now we just have to put all of this scary looking thing here in for that ES. So we would have times S times E total over S plus all those K's. K2 plus K minus 1 over K1. Give you just a moment to write that out, and then I'll explain the importance of that. I'm going to start moving some of the other things that we'd already done up. So the reason why that's important, this term right here, all these little K's, is simplified because it becomes Km. Because capital K is related to all those little individual rate constants. But it's just not as simple as saying it's one of them divided by another. It's an amalgam of all of these, because all of these little tiny ones are little individual rate constants, and this is an equilibrium constant. So that's why this entire thing becomes simplified. I'm just going to write the bottom first. We have the S on the bottom plus a Km. See, it becomes much more simple. It just shows you the equilibrium constant, and from the equilibrium constant, it just shows you the complexity of all the little individual rates, how it affects it. On the top, I'm just going to rearrange it just ever so slightly to put K2 times E total right by each other, because remember, 1 times 2 times 3 is the same thing as saying 1 times 3 times 2 times S. This right here, this E total times K2, That's Vmax. So now we can say that V is equal to Vmax times S over S plus Km. And the importance of this is it's going to give you that hyperbolic function. Now this is only true, that's a V, it's supposed to be V. Once again, if it follows Michaelis-Menten equation, kinetics. Anything that's more complicated, I just want to point out, anything that's more complicated, like if we had an EP in there, this Km would have even more little k's in there. And even the Vmax itself, it may not just have a single k. It may be multiple k's, like plus and divided by, much more complicated than whatever it is. And so what this tells you, and what we'll pick up on the next class, is it's going to let you get an idea of affinities. This tells you how quickly, but neither one of them tell you how efficient. Okay, so I'm going to go ahead